Welcome to Lecture 5.1, Groups Acting on Sets. This series of lectures is all about the concept of a group action. Intuitively, a group action occurs when a group G naturally permutes a set S of states. And we'll see shortly what this naturally permutes means in formal mathematical terms. But first, let me give you some examples of group actions that we've seen before. Start out with the Rubik's Cube group. That's what we saw in the very first lecture. This consists of 4.3 times 10 to the 19 or so actions. Again, these are actions, but they permute the same number of configurations of the cube. So there's two things at play here. There's these actions and there's these configurations. We defined a group to be a collection of actions, but up to this point we've sort of ignored the idea of configurations, or we've acknowledged them, we just haven't done anything with them. Next, we have the group D4, as we know, consists of the 8 symmetries of the square. Now the symmetries are actions, and they permute the 8 configurations of the square. Group actions help us understand the interplay between the actual group of actions and the sets of objects that they rearrange. There are many other examples of groups that act on sets of objects. We will see examples when the group and the set have different sizes. In these two examples above, there was a bijection between the actions and the configurations. But in general, this need not happen. There is a rich theory of group actions, and it can be used to prove many very deep results in group theory. It's going to be this extremely useful toolbox. So we'll build up this collection of theory on these groups permuting sets, and then we will apply them in very surprising ways and get some very powerful mathematical results on topics that seem in no way related to a group action. Let's start with a familiar example. The dihedral group, D4, can be thought of as the 8 symmetries of the square. And I'm going to write the square like this. So there are numbers in each corner, 1, 2, 3, and 4, and I'm going to color code the numbers as well. There is a subtle but very important distinction to make between the 8 actual symmetries of the square and the 8 configurations of this square right here. For example, the 8 symmetries, alternatively actions, can be thought of as the following familiar 8 elements: the identity, r, or 90-degree rotation, r squared, a 180 rotation, r cubed, a 270 rotation, and so on. However, the 8 configurations or states of the square are the following. So here I'm assuming that my square is like a smartphone, that when I rotate it, the numbers stay right side up. When we were just learning about groups, we made an action diagram, just a Cayley diagram. The very first thing we did, pretty much. The vertices corresponded to the states, these configurations, and the edges corresponded to generators. And then we said, well, the vertices also correspond to elements or actions in the group because paths corresponded to actions. So we had this bijection between configurations and symmetries. Here is the action diagram for the group D4. And it's just a Cayley diagram. Nothing new about this. Let me remind you how we constructed this bijection between configurations and actions. Way back in the beginning of the course, we picked a configuration and declared it to be the solved state. For example, this configuration right here, 1, 2, 3, 4, in clockwise order. Then, every other node in the Cayley diagram corresponded to a configuration, and we said we can associate that with the action that we get when we follow the path from the solved state to that node. For example, this configuration in the upper left-hand corner corresponds to the flip following the blue edge. This configuration in the bottom right-hand corner corresponded to blue, red, red. In other words, F R squared. The resulting diagram was, of course, a Cayley diagram. In this chapter, we will skip the step of declaring a certain configuration to be the solved state. This will free us from the bijection between configurations and actions, and it will allow us to look at groups that permute or act on sets of different sizes. The novel idea of group actions, I'll say it one more time, though it might be a little overkill, is in all of the examples we've seen. In the beginning of the course, we had this bijective correspondence between actions and states, and this need not always happen. For example, suppose we have a size 7 set consisting of the following, I'm going to call them binary squares, right here. Now, of course, there are 16 so-called binary squares, but let's just suppose I have a set of 7 of them. I don't need all of them. This will do. The group D4 acts on the set S as follows. It's the natural way that you would expect this group to permute these squares. For example, if you rotate, so rotating is the red arrow and flipping is the blue arrow, if you rotate this square by 90 degrees, you get down to that square, and if you rotate it again, let's just say clockwise, you get back here. So there is this two-way red arrow from here. Let's go over here, this 0, 0, 1, 1. If you rotate this 90 degrees clockwise, you get to this configuration, 1, 0, 0, 1. If you rotate it again, you get down here, and it takes 4 rotations to bring it back where you started. What about flipping it? Let's say that this flip, F, is a horizontal flip, so it flips it about a vertical axis. Well, if you flip this square about a vertical axis, it sends it to itself. So this blue arrow is a loop. However, if you flip this square, 1, 0, 1, 0, about a vertical axis, it does not fix it. It sends it to this square in the lower right. Similarly, if you flip this checkerboard 1, 0, 1, 0, 1, about the vertical axis, it sends it to this other checkered board 1. And finally, this lone square, 0, 0, 0, 0, is fixed whether you rotate it or flip it. So this action diagram describes what you get as you rotate and you flip these squares according to the group D4. Now, the action diagram above has some properties of Cayley diagrams, but there are some fundamental differences as well. Let's say a few words about some things that are preserved. Well, like in Cayley diagrams, if you want to know what happens when you do a sequence of actions, you can just follow the paths. For example, what happens when you do R squared? When you rotate something 180, you just start at a node and you follow the R arrow twice. Do red, red, it gets down here. Over here, if you do red, red, you get back to itself. Or if you want to do, say, rotate and then flip. And pick any node, follow the red arrow and the blue arrow, and that tells you what happens when you apply this group element, or this action, to that configuration. So that's similar to Cayley diagrams. Another similar property is that at every node there is exactly one outgoing arrow of each type. And that also is perfectly natural, because at each node you can apply each generator. But as I've said, there are some fundamental differences. For example, in a Cayley diagram, you are never going to have a case where you have a blue arrow being a loop on one node, but not a loop from another node. That's never going to happen. You're never going to have this red path that leads into a 4 cycle over here, but a 2 cycle over here and a 1 cycle over here. In fact, we proved one of these things in one of our first lectures. We proved that if some arrow is a loop on some node, it has to be a loop on every node. That was our very first logical mathematical proof. So that is a fundamental difference. Other differences. Well, this action diagram is not connected. You can't get from the state 0, 0, 0, 0 to this state 1, 1, 0, 0. There's no way to do it. Now, I'm going to give you another way to think about what we're doing. And this is not in any book that I've ever seen. This is my own way of thinking of it. It's an analogy that I made up, and I hope it helps. So I want you to think of there being a group switchboard. So here's what I mean by that. Suppose we have a switchboard for G where every element has a button. So in the case of D4, there are 8 buttons in front of you, 1 for each element. For every element A in G, if you press the A button, it rearranges the objects in our set. In fact, it's a permutation of the set. Let's call it phi of A, because that's what happens when you apply an action to a collection of objects, is it permutes the objects. Now, if B is another element in the group, then there is a B button somewhere, and if you press the B button, that rearranges the objects in S in a potentially different way. Let's call this permutation phi of B. Finally, there's another element, A times B. AB is an element in G. That has a button. And here's the key property. We require that pressing the AB button yields the same result as pressing the A button followed by the B button. In other words, in formal mathematical terms, that means phi of AB, this permutation, is equal to phi of A times phi of B for all elements A and B. Does that look familiar? This property? Yep, that has something to do with the homomorphism, and we'll figure out exactly what. So let's let Perm of S be the group of permutations of S. So S is a set of objects. It might be a set of binary squares. So there's a corresponding group of permutations. Now, this does not need to be a finite group. It could be infinite. But if it is finite, and if it has order n, then this permutation group is naturally isomorphic to the symmetric group Sn. I typically think about Sn as the permutations of the set of numbers 1 up to n. At last, here's our formal definition. A group G acts on a set S if there is a homomorphism phi from G into the set of permutations of S. So think about how that agrees with what we did above. So let me draw a picture now. So we have this A button here, we have the B button, we have the AB button. We're going to have the identity button. We might have an A cubed B squared button. And so all of these things have a button. So we have this big switchboard in front of us. And there's going to be other buttons corresponding to other group elements. And of course, this button is only different from these buttons if this group element is different from these group elements. So when we push a button that rearranges our set, think in your mind, it rearranges the set of binary squares. So if we push the A button and then push the B button, that's the same thing as pushing the AB button. So when we push a button, we get a permutation. In other words, that is a mapping that sends A to some phi of A. That's some mapping phi. So what is phi? Phi is a function that inputs a group element A. So the domain of phi is something in our group, and the codomain of phi this is a permutation. So this is a permutation of our set S. So phi is indeed a map from G to perm of S, and it has to satisfy this property. Phi of AB equals phi of A times phi of B. That is the definition of a group action. Let's return to our binary square example, where pressing the R button and then the F button permutes the set S as follows. Well, that's what you get when you press the R button. So it's going to fix this. It's the permutation that swaps these two squares, and it's the permutation that is this 4 cycle that rotates these. This is a permutation of the set of 7 elements. Next, phi of F. When I press the F button, this element gets fixed, these two squares get swapped, this gets fixed, this is fixed, and these two are swapped like that. Observe how these permutations are encoded in the action diagram. I'm essentially overlaying these permutations on top of each other. So when I overlay these nodes and these nodes, because they're the same, I get this component. And when I overlay this with these 4, I get this. And I should say that here I'm drawing the blue loops to emphasize that these are fixed, and here I'm drawing red and blue loops. Up here I did not do that. Just for brevity, instead of drawing self loops, I just drew nothing. So if you want, you can think of there really being a self loop there and a self loop there. And similarly, that's a loop and that's a loop. But anytime there's nothing going out, you can assume it's a fixed point. Now, before we go any further, I need to address a small technicality. That is the difference between something that's called a left group action and a right group action. And I say that this is an annoyance, but it's something that we can deal with. So, as we've defined group actions, pressing the A button followed by the B button should be the same as pressing the AB button. However, sometimes it has to be the same as pressing the BA button, not the AB button. This is best seen by an example. Let's consider conjugation. In the next lecture, we'll see some examples of how conjugation can arise in a group action where the group is acting on maybe another group, on itself, or maybe on a set of subgroups. So let's conjugate by A, and when I say conjugate, let's do it so we multiply the element on the left and its inverse on the right. So if we conjugate by A and then by B, notice that that is not the same thing as conjugating by the element AB. In fact, that's conjugating by the element BA, because there's BA, and this is the inverse of BA. So here, pressing the A button and then the B button is actually the same as pressing the BA button. In contrast, let's conjugate the other way. So we multiply on the right by the element A and on the left by its inverse. Now, if we conjugate by A and then conjugate by B, that is the same as conjugating by AB. So in other words, pressing the A button followed by the B button is the same as the AB button. We say that the former case is a left group action and the latter case is a right group action. And at this point, it's probably not clear why one of these is left and why one of these is right, or, what's so left about this example and right about this example, we will see that shortly. In fact, we'll see it right now. Some books forego our phi notation, where phi is that homomorphism, and instead they use notation like this. So if you have an element S in your set and you apply the action of A, in this case conjugating by A, you can write that as A dot S. So you're applying the action A to the set element S. So this is a group element, that's a set element. Now, of course, multiplying this on the left is just a choice, it's an arbitrary choice. We could instead take our element in the set, and when you apply the action of A, you're multiplying on the right. So you could denote that as S applied, or A applied to S. Now, if you multiply on the left, then it's only natural that S applied, well, I should say, start with S, then apply H, then apply G, because you want this to be associative, you want parentheses to be optional, permitted anywhere, required nowhere. That has to be the same as G times H applied to S. Whereas if you're doing this on the right, then S, starting with S, then applying G, then applying H, should be the same as starting with S and then applying GH. So using this notation, it's easy to see why this on the left, the G button, the H button followed by the G button should be the GH button, why this is said to be a left group action. It lines up with this example. Whereas on the right, applying the G button and then the H button should be the same as the GH button, why that is a right group action. It aligns with this example up here. Now, I like both of these notations. I like this notation down here because it's simple. You can see H applied to S and then G applied to that. But I also like this notation up here because it really gets the point across that phi of A is a permutation. So I will often do a little mixture of these notations. I will write things like, instead of G.H.S, I will write phi of G times phi of H times S. So we're starting with S and we're applying phi of H and we're applying phi of G. That's the same as phi of GH applied to S. But if it's a right group action, I will write S and then dot phi of G dot phi of H, and it's understood that that is the same as S dot phi of HG. So as with groups, the dot will be optional. I chose to put it in here because it seems like there should be a space between the S and the phi, whereas I didn't feel like that dot was as necessary over here because there's an end parentheses right before the S. As I said in the previous slide, there are two very different ways to define a group action. One of them is how we did it, very simply, as a homomorphism from the group to the permutations of our set. Let's call this phi. So that's one way to define a group action. Another way that other books use, which involves that dot notation, is as following. And I'm going to show you here just so you see it in case you encounter it elsewhere. And I'm only going to define a right group action like this instead of a left group action. So a right group action can be defined as a mapping from G cross S to S. So think of it as the input being a group element applied to a set element. So a permutation of a set element, what happens? It spits out another set element. So this is the action that sends this set element to that set element. It can be written as the input being an ordered pair of A and S gets sent to S dot A. Now you have to have a few basic requirements. You need S dot AB to be equal to S dot A dot B for all group elements A and B and all set elements S. And finally, you need the simple requirement that S dot E equals S. In other words, the identity group element has to fix everything in your set. This is how we define a right group action. A left group action can be defined very similarly. Basically just reverse this, stick it up to the mirror, and pretty much all of the theorems for left group actions hold for right group actions. Usually, if there is a left action, there is a related right action, like how we saw with conjugation in the previous slide. We could define it one way so it was a left action, but there's a very natural way, just as natural way to do it so it's a right action. We will usually use right actions, and this is actually different than most books. Most books will use left actions, and that's because it is more natural to start with a set, and then it's arguably more natural to do things like apply your group elements to the left of a fixed set element like this. However, because this series of lectures and this whole class deals with Cayley diagrams, now a Cayley diagram is what you get by thinking of the group action as a right action. And maybe that's not quite clear, but I encourage you to think about it. When we construct a Cayley diagram, we are multiplying things from left to right. A path in the Cayley diagram is what you get by reading your group elements from left to right. So I will usually write things like S dot phi of G to denote the element of S that the permutation phi of G sends S to. Now, many books will write it like this up here. They omit the phi. I like to have the phi in there. It just helps to remind me that this is indeed a permutation. G is a group element. Sometimes if you have A's and S's both here, it's easy to forget if A is a group element or a set element. So if I write something like this, hopefully it should be very clear. And if we have a left action, we'll write something like this, phi of G dot S. So again, it's a little bit different than most books because we usually favor right actions, and we also are a little more pedantic and we usually keep the phi around where most books don't. Finally, I want to finish with how to think about Cayley diagrams as action diagrams. I mentioned this in a sentence or two on the previous slide, but now I want to show you a picture. So every Cayley diagram can be thought of as the action diagram of a particular right group action. And as before, we will illustrate this with an example. Consider the group D4. And now I want to say it acts on itself. In other words, the set is also D4. So the group D4 acts on itself. It acts on the set D4. And here's how we define our action. Suppose that pressing the G button on our group switchboard, this is the mental picture I want you to have, multiplies every element in here on the right by G. Here is the action diagram right here. Now let me do an example. Let me explicitly write out an example. So here's E, here's R squared, here's R cubed, here's F, here's RF, R squared F, and R cubed F. Now let's push one of these buttons. We have a group switchboard over here where every group has a button. Let's press the F button. Oops. So the F's got a button. Let's press it. So what happens? So E, oh by the way, pressing the F button, as we said, multiplies every element on the right by F. So E gets sent to, what's E times F? That's just F. R gets sent to RF, R squared gets sent to R squared F, R cubed gets sent to R cubed F, F gets sent to the identity, RF gets sent to R, RF squared gets sent to R squared, and R cubed F gets sent to R cubed. So what's happening? These two swap, E and F swap places, these two swap places, these two swap, and these two swap. This is a permutation of the 8 group elements. And which permutation is it? Well, at every node, just follow the blue arrow. So this is a new way about thinking of a Cayley diagram as a group action. We say that G acts on itself by right multiplication. And of course, this can happen, this works for any group, finite or infinite. In the next lecture, we will state and prove and analyze what probably is the most important basic theorem on group actions. It's called the orbit stabilizer theorem, and it presents a dichotomy between the sizes of the connected components of an action diagram and the sizes of the subgroups of the group that fix certain elements in the action. After that, we will see a lecture on a bunch of examples of group actions involving groups acting on other groups or other features of groups. For example, a group can act on itself, meaning the set is also the group, by left or right multiplication, or it can act on itself by conjugation. A group can act on its set of subgroups by conjugation. It can act on its set of left or right cosets by left or right multiplication. And in defining these actions and studying them, often we get new characterizations of old familiar objects, and in many cases we get almost for free or for very little work proofs of very deep theorems on group theory that are seemingly unrelated to the actions at hand. So group actions are very powerful and very cool, so I hope you stay with us.